Okay, we are going to talk about derivatives of exponential functions today. And so here we have an exponential function. B is just some positive real number. It might be 2 to the x, it might be 3 to the x, it might be 10 to the x, it might be 2.97325 to the x. And I just want to figure out what the derivative is. And our go-to way of doing this is use the definition of the derivative. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. That's equal to the limit as h goes to 0. I'm going to omit that because I'm lazy. B plus h minus b to the x all over h. Okay, I'm going to use my rules of exponents here to say that this is equal to the limit of b to the x times b to the h minus b to the x all over h, which equals to the limit. Oh, look. Hey, I can factor a b to the x out of both of these. So that's equal to the limit of b to the x times b to the h minus 1 all over h. And remember, this is the limit as h goes to 0, in spite of the fact that I've been writing it. The b to the x has nothing to do with the h, so I'm just going to pull this outside times the limit as h goes to 0 of b to the h minus 1 all over h. So if I could just figure out what this is, then I could figure out what the derivative is. It's just itself, b to the x times this thing. Well, I'm going to rewrite things a little bit. So I'm going to rewrite stuff times the limit as h goes to 0. Well, the first thing I'm going to do is leave the h on the bottom alone. Next thing I'm going to do is this b to the h. I'm going to rewrite this as b to the 0 plus h. I can certainly do that. And then I'm going to subtract off 1, except I'm not going to write it as 1. I'm going to write it as something that's equal to 1, which is b to the 0. And so I can do that. It's completely equal. And the advantage of that is if you look at this quotient right here, it looks exactly like this quotient right here, except with x's instead of, or except with zeros instead of x's. And this was equal to f prime of x. So whenever I have an x here, I get f prime of x. If I have a 0 there, that means I get f prime of 0. And so this is revelation number 1. So I know what the derivative is as long as I know what f prime of 0 is. Well, what does that mean graphically? Well, the graph of b to the 0, or b to the x, looks something like this. And this is actually f of x is equal to that. That's almost legible. But remember, f prime of 0 is a tangent line at 0. So the slope of this line is equal to f prime at 0, which is the one that goes through that point. So if I want to find the derivative anywhere, all I do is I go up. If I want to find the derivative at 6, I go over 6, go up, find the y value, that's b to the 6th, and I multiply it by the slope of this line. So that's really pretty cool. Now, if you're curious, you might want to say, how can I make this derivative as nice as possible? Well, maybe I could find one of these exponential lines, because remember these exponentials, here's like 2 to the x, here's like 10 to the x, and they kind of go through continuously. And so the slope of the tangent lines changes. So for 2 to the x, the slope might be roughly like that. For 10 to the x, the slope is like that. And if we did like 9.5, it'd be a little bit less shallow, less steep than that. So the key thing is, if we could find there must be some number between 2 and 10 where the slope equals 1. We'll call that number e, and that's how we're going to get e to the x.